What if everything you know about the universe is merely a fragment of a deeper, hidden reality? From the tiniest particles to the very fabric of space itself, the cosmos remains a mystery we've barely begun to unravel. Some scientists suggest our reality is not singular. Unseen dimensions, alternate worlds, or even the universe itself as a mathematical construct may hold the answers. These ideas aren't just speculative. They challenge the boundaries of what we consider reality. Why does mathematics so perfectly describe the universe? What if the rules we rely on are merely shadows of a deeper truth? Today we aim to tackle the questions that transcend human understanding. The complexity of the universe has inspired numerous unconventional theories, each attempting to challenge our understanding of reality. Among them are the simulation hypotheses, the holographic principle, and Brane cosmology, all offering radically different perspectives on the nature of existence. For example, the simulation hypothesis posits that our universe is not a physical reality, but a complex digital construct. Popularized by thinkers like Nick Bostrom, this hypothesis suggests that an advanced civilization could create simulated worlds indistinguishable from reality. The idea becomes increasingly plausible with the rapid advancements in computer simulations and virtual reality. Consider this. If it becomes possible to simulate entire worlds with conscious beings, the number of simulated realities could far exceed the number of physical ones. By this logic, the probability of us existing in a simulation rather than base reality increases. While this hypothesis remains unprovable, it has sparked debates among scientists and philosophers about the nature of free will, ethics, and even the limits of science. The holographic principle, on the other hand, takes a fundamentally different approach, suggesting that our entire three-dimensional universe could be encoded on a two-dimensional surface. This idea stems from black hole physics, where researchers like Gerard 't Hooft and Leonard Susskind propose that the informational content of a black hole resides on its event horizon rather than its volume. When extended to the entire universe, this implies that everything we perceive as volume in space is, at its core, a projection. Recent studies in quantum mechanics and string theory have explored this possibility, and some models have shown that the mathematics of a two-dimensional universe can indeed replicate the physics of a three-dimensional one. This concept deeply impacts our understanding of reality, raising questions about whether our perception of depth is merely an emergent illusion. Brane cosmology is another intriguing idea derived from string theory, which envisions our universe as a three-dimensional brane, short for membrane, embedded in a higher dimensional hyperspace. According to this concept, other branes could coexist, separated by imperceptible dimensions. Interactions between these branes, such as collisions, might even explain phenomena like the Big Bang. This idea opens up fascinating possibilities. For instance, gravity might appear weak in our universe because it leaks into these extra dimensions. Moreover, if branes can interact, one might wonder whether contact with another brane could explain phenomena we currently don't understand. Let's delve into a less conventional idea: the one-electron hypothesis. Proposed by physicist John Wheeler a bold and unconventional concept regarding the fundamental principles of our universe. According to Wheeler, every electron in the universe could be the same electron, traveling along a single continuous trajectory through time and space. This radical notion is based on the concept of world lines, which represent the path of an object in spacetime. In physics, world lines trace the trajectory of a particle or object as it moves through space and time. Unlike the conventional idea of tracking an object's movement in three-dimensional space, world lines incorporate time as a fourth dimension, creating a continuous representation of a particle's existence in spacetime. Wheeler's thought experiment emerged during a conversation with his colleague, Richard Feynman. He speculated that an electron traveling backward in time could appear as a positron, the antimatter counterpart to an electron. If true, every electron in the universe could originate from the same singular entity, traveling forward and backward through time. Wheeler envisioned the electron's trajectory as a loop in spacetime. Moving forward in time, it behaves like a regular electron, and moving backward in time, it manifests as a positron, the antimatter twin of the electron. The looping trajectory would weave a tapestry where every observed electron in the universe corresponds to a segment of this unified, interconnected path. In this system, the world line of this single electron twists and turns through space-time, intersecting countless times. And at each intersection, a particle appears as an electron or positron depending on its temporal direction. The unusual concept creates an infinite number of manifestations of the same particle without requiring new particles. This hypothesis, though highly speculative, offers a remarkably simple explanation for why all electrons possess identical properties, such as charge and mass. Wheeler's idea, however, raises questions about the mechanisms enabling such phenomena and the symmetry, or lack thereof, between electrons and positrons. Richard Feynman expanded on Wheeler's concept, proposing that antimatter could be interpreted as ordinary matter moving backward in time. This interpretation, foundational to quantum electrodynamics, suggests that particles like positrons are indistinguishable from electrons traveling in reverse temporal order. This perspective aligns with Feynman diagrams, where particles and their antiparticles can interchange roles depending on the direction of time. While this one electron hypothesis is not a mainstream theory, the concept of time reversal remains a cornerstone of modern physics, offering insights into particle interactions and symmetries in quantum fields. This hypothesis suggests an extraordinary level of interconnection among all particles. If true, it would mean the fabric of the universe is unified through a single particle traversing time. This interconnection implies the existence of a deeper fundamental structure governing all matter, potentially challenging traditional distinctions between individuality and universality in physics. However, this theory faces significant challenges. For instance, the observable universe contains far more electrons than positrons. If all electrons were manifestations of one particle, this asymmetry would require an explanation. The lack of corresponding positrons equally complicates the hypothesis, keeping it largely in the realm of thought experiments rather than empirical science. Now let's explore the equally fascinating concept of superfluid spacetime, which envisions the very fabric of the universe as a superfluid liquid, a state of matter with unique, nearly frictionless properties. This idea emerges as a potential bridge between two of physics' most profound theories: Einstein's general theory of relativity and quantum mechanics. To begin, let's recall that space-time is a four-dimensional structure in which events in the universe unfold. General relativity describes space-time as a dynamic entity that can bend, stretch, and deform under the influence of mass and energy. Massive objects, such as stars and black holes, create distortions in space-time that we perceive as gravity. While general relativity successfully explains large-scale cosmic phenomena, it struggles to integrate with quantum mechanics, which governs the behavior of particles on microscopic scales. Quantum mechanics treats space-time as a chaotic, probabilistic field filled with fleeting particle interactions, rather than a smooth continuum. This is where the analogy with the superfluid offers an intriguing perspective. From this viewpoint, space-time behaves like a superfluid, a special phase of matter with nearly zero viscosity. Superfluidity is best known in helium-4, which when cooled to near absolute zero transitions to a state where it flows without resistance and exhibits counterintuitive behaviors, such as climbing walls or forming quantum vortices. Quantum vortices are tiny, stable whirlwinds in superfluids, where rotation occurs in fixed, quantized steps. Unlike ordinary vortices, they experience no friction and have sharply defined cores due to quantum effects. If space-time operates like a superfluid, its quantum properties might manifest as tiny oscillations or waves akin to excitations in a liquid. These oscillations could correspond to elusive quantum gravitational phenomena that physicists have long sought to reconcile with relativity and quantum mechanics. For instance, gravitational waves detected by LIGO may represent microscopic expressions of such superfluid dynamics in spacetime. The superfluid spacetime hypothesis provides a framework for reconciling the smooth, continuous nature of spacetime and general relativity with the probabilistic, fluctuating nature of quantum fields. In this model, the apparent smoothness of spacetime on large scales is due to its superfluidity, while its quantum properties become evident at microscopic scales. Quantum vortices in superfluid helium bear striking similarities to predicted structures of space-time singularities, such as those in black holes. These vortices could serve as a physical analogy for understanding the granular quantized structure of space-time at the Planck scale, the smallest scale of space, time, and energy, where quantum mechanics and gravity merge, and our current physics breaks down. In other words, it's the size of the building blocks of the universe. Superfluid liquids such as helium-4 and helium-3 serve as experimental platforms for studying potential spacetime behavior. Researchers have observed these liquids mimicking phenomena seen in astrophysics and cosmology, such as quantum turbulence, wave propagation, and even analogs of event horizons. Moreover, the behavior of quantized vortices and rotating superfluids resembles the rotation curves of galaxies, hinting at connections between micro and macro scales. By studying these systems, scientists continue to gain insights into how spacetime might behave under extreme conditions, such as near black holes or during the early moments of the Big Bang. Naturally, speaking of bold ideas, it's impossible not to mention the mathematical universe hypothesis, proposed by physicist Max Tegmark. This theory posits that the universe itself is a mathematical structure. According to this idea, everything in the cosmos, from particles to galaxies, is not merely described by mathematics, but fundamentally consists of it. From this perspective, the laws of physics and even reality itself arise from the properties of mathematical objects. The roots of this idea trace back to antiquity. Philosophers like Pythagoras believed that numbers and mathematical relationships underpin all of reality, famously declaring that all is a number. Plato expanded this notion, suggesting that mathematical forms or ideal objects exist in a timeless realm, shaping the physical world as imperfect reflections. In modern times, Max Tegmark revived this philosophy, asserting that every aspect of the universe corresponds to mathematical structures. And Tegmark argues that at its deepest level, the universe is not made of stuff, but is pure mathematics existing independently of human thought. This hypothesis finds support in the striking mathematical patterns observed in nature. Consider the hexagonal structure of honeycombs, which reflects maximum packing efficiency, a concept rooted in geometry. Similarly, cicadas emerge in prime-numbered year cycles, such as 13 or 17 years, minimizing overlap with predators, a biological phenomenon tied to a number theory. In space, planetary orbits follow precise elliptical trajectories described by Kepler's laws, which are inherently mathematical. These examples demonstrate how nature appears to adhere to principles pointing to a profound connection between reality and abstract mathematics. One of the strongest arguments supporting this hypothesis is the remarkable effectiveness of mathematics in describing and predicting physical phenomena. For instance, Einstein's equations of general relativity predicted the existence of gravitational waves decades before their discovery. Similarly, the framework of quantum mechanics relies entirely on abstract mathematics to explain the behavior of particles on subatomic scales. This power of prediction raises an intriguing question. If mathematics is merely a human intervention, why does it align so perfectly with how the universe operates? Critics argue that while mathematics is a powerful human-made tool, it is something we use to interpret the universe rather than necessarily reflect its fundamental nature. They propose that the patterns we observe may arise from physical laws rather than being purely mathematical constructs. Moreover, some point out that not all phenomena can be perfectly modeled mathematically, suggesting potential limitations of this approach. Others question the existential implications of the hypothesis. If the universe is mathematics, what does that mean for the physical perception of reality? Last but not least, our list concludes with the multiverse theory, which posits that what we perceive as the universe might be just one part of a vast collection of different universes. These other universes, often referred to as parallel or alternate, may differ in scale, structure, and even the fundamental laws of physics. To classify these ideas, the aforementioned physicist Max Tegmark introduced 4 distinct levels of the multiverse, each representing a unique expansion of our understanding of reality. At level 1, the multiverse consists of regions of space beyond our observable horizon. According to cosmological models, the universe is potentially infinite. If so, there exist countless regions beyond our visible space where the same physical laws apply, but with different initial conditions. In these regions, galaxies, stars, and even forms of life could exist vastly different from anything in our observable cosmos. Level 2 arises from the theory of eternal inflation. This theory suggests that rapid expansion of space gives rise to bubble universes, each with its own physical constants and dimensional structures. For example, one bubble might have stronger gravity, causing stars to burn out quickly, while another might have entirely different dimensions, making life as we know it impossible. These universes exist independently of ours and may remain forever inaccessible, separated by vast, inflating regions of space. Level 3 stems from the many worlds interpretation of quantum mechanics. This idea suggests that every quantum event creates a branching of realities, with every possible outcome occurring in its own separate universe. For example, when a photon passes through a slit, it takes all possible paths, each in its own universe. These parallel universes coexist, but are limited in their interaction. This perspective not only broadens the scope of reality, but also provides a framework for understanding quantum phenomena that appear probabilistic in our universe. Level 4 represents the most speculative level. Universes governed by entirely different mathematical structures. In this scenario, even fundamental concepts like space, time, and matter may not exist as we understand them. These universes might operate under completely alien rules, rendering them incomprehensible from the standpoint of our mathematics. This level is directly tied to the mathematical universe hypothesis, which asserts that all mathematical structures exist, and each corresponds to its own unique universe. Level 4 encompasses the idea that our universe is just one of an infinite number of mathematically possible realities. Here, the hypothesis of the mathematical universe serves as the philosophical foundation of the theory. If all mathematical structures exist independently of human thought, it follows that every conceivable mathematical structure can describe its own unique reality. This would encompass universes of all levels, linking the multiverse to the fundamental nature of mathematics. This connection raises profound questions. If our universe emerged from a mathematical structure, what determines its specific characteristics? And if alternate universes are described by different mathematics, could they ever interact with or influence our reality? Unconventional hypotheses, whether it be the multiverse, superfluid spacetime, or the mathematical universe, challenge the boundaries of both scientific and philosophical thought. Critics highlight the lack of empirical evidence, as many of these theories are untestable with current technology. However, their conceptual strength lies in how they integrate mathematics, physics, and philosophy to reimagine our understanding of existence. These ideas prompt us to ask, are we nearing an understanding of the true nature of reality? Or do these hypotheses merely broaden our misconceptions? Perhaps to understand reality, we must first define what we mean by it.
At some point of our lives, we have probably all wondered if we are alone in the universe. It would seem that in our own or in other distant galaxies, there are so many planets that revolve around numerous stars. So why have we still not encountered any traces of extraterrestrial life? But what if advanced alien life forms have been around for a long time, and they're simply hiding? According to the dark forest hypothesis, technologically advanced civilizations outside of the solar system may already be thriving. However, they have no intention of making contact because they are either cautious of potential attacks from other civilizations, or they may be indeed preparing to attack. Today, you'll learn about the dark forest theory and why you should probably be afraid of being heard by someone. 1. The dark forest hypothesis, the author and original source. The author of the dark forest hypothesis, DFH, is science fiction writer Liu Cixin. It's worth noting that this is not a scientific theory, and it's not based on any concrete evidence. In 2008, Liu Cixin published his successful fiction novel titled The Dark Forest. The dark forest theory was first outlined in this book. The gist of the theory is that every civilization on a cosmic scale seeks to obtain the resources necessary for its continued survival. Therefore, any extraterrestrial life hides in order to not be destroyed by another civilization, and also in order to be able to attack and ensure its own survival. So why is this theory called the dark forest hypothesis? In his novel, Liu Cixin compares this to precarious coexistence to a forest inhabited only by hunters. The author paints civilizations as metaphorical armed shooters in a dark forest, who silently move forward, afraid of being discovered by fellow hunters. If one hunter managed to find another, it's in their best interest to attack first before the enemy does the same. Based on this, we can name several ideas that are promoted by DFH. First one is that hypothetically, alien civilizations exist, but they are in hiding due to the risk of being attacked by others and losing acquired resources, such as inhabited planets. Within the construct of the dark forest hypothesis, survival as the basis of every civilization is known as the chain of suspicion. This phenomenon is caused by insufficient communication, which leads to mistrust as a direct result. The second idea is that a civilization that gives away its location by actively transmitting, say, radio signals, could be captured or destroyed by others for resources. The third concept is that fellowship in this type of system is exceedingly rare, since every civilization strives above all to survive through expansion. However, a treaty is possible if the terms are beneficial to both civilizations. Liu Cixin represents the universe as a battlefield for limited resources, where an alliance is practically impossible. Finally, it's important to note that in Liu Cixin's hypothesis, these hunters are analogous to civilizations with a high level of technological advancement. Therefore, if any civilization is not sufficiently developed to announce itself in space, it will either go unnoticed or it may become easy prey. 2. DFH is an answer to the Fermi paradox. As you may already know, in 1950, famous physicist Enrico Fermi, when discussing the phenomenon of flying saucers with his colleagues, unexpectedly asked, "Where is everyone?" referring to examples of extraterrestrial life, which marked the beginning of the famous Fermi paradox. We discussed it in detail in this video on our channel. Fermi assumed that if our galaxy formed several million years before the birth of mankind, then it is possible that other civilizations could have emerged during this period, much older than Earthlings. Therefore, the Milky Way galaxy should be full of civilizations, which could pick up our signals due to their much more advanced technological development, as well as travel through the galaxy. However, so far we have not seen any traces of alien activity. Why haven't they visited Earth yet or come close to our planet? To determine the potential number of extraterrestrial civilizations that exist within our galaxy, the famous Drake equation was derived in 1961. However, we cannot use it to learn why alien creatures have not left any signs of their life. Therefore, at the moment, the Fermi paradox only has theoretical explanations. Additionally, according to physics professor Adam Frank, the probability that Earthlings are the only civilization in the universe is very small. 1 in 10 billion trillion, which is to say 1 times 10 to the 22nd. The professor suggests that our evolution was not unique and other civilizations could potentially have existed before us or even much longer before us. There are more than 70 hypothetical solutions to this issue, one of which is the dark forest hypothesis. Of course, we cannot check the veracity of DFH due to our current technological limitations. However, Liu Cixin's theory provides a logical explanation as to why we still haven't picked up a single alien signal or found any clear signs of life on other planets. It's simply dangerous for other civilizations to betray their location for fear of invasion. Although this hypothesis presents very clearly defined ideas, DFH still has some inaccuracies. For example, if other civilizations exist, then they must differ from ours when it comes to the level of development due to different periods of origin, as Fermi pointed out. This means that there may be civilizations of our technological level or higher that actively search for alien life or study their own systems just like us, because they don't see it as a threat. Therefore, we may not be the only ones sending signals out there, because civilizations do not necessarily develop in fear of detection if they have not experienced confrontation. 3. More about the assumptions of dark forest hypothesis. The idea of capturing other territories and the possible destruction of the first civilization on a cosmic scale is reminiscent of our historical experience on Earth, namely colonization and wars. There are a lot of reasons why people conquer and establish power over other nations. However, in most cases, such as during the colonization of Africa by the Europeans in the 19th century, the main motivation were land and natural resources. The rapid industrial development in Europe required more resources, which were abundant on another continent. Therefore, the colonization of Africa contributed to the development of European countries, but the African land and its population suffered from this expansion. The DFH offers the same colonial model as the reason why one civilization would attack another. We're still pursuing the goal of expansion for the continued survival of mankind, studying exoplanets and other star systems, and planning the colonization of Mars. The red planet is also rich in natural resources that are needed for technological development. Therefore, if we assume that another civilization pursues the same goals, we may have to fight for lands that could serve humanity. Otherwise, our survival would be under threat because, according to this hypothesis, survival and the necessary resources are crucial for the preservation of the species. In addition to the need to replenish a limited resource, there are other reasons for the aggressive behavior by civilizations. For example, as we've already said, the DFH introduces a concept known as the chain of suspicion. This concept is closely related to another aspect of this hypothesis, which is known as the technological explosion. The gist of the chain of suspicion is that it's impossible for civilizations to know whether others are benevolent or hostile. These doubts can lead to preemptive attacks and self-defense. According to the researcher Chao Yu, this chain can only emerge between civilizations with the same level of technological development, since they can likely objectively assess their own and other people's capabilities. Thus, if there is a significant gap in their respective levels of development, the chain cannot be formed. Technological explosion describes the ability of cosmic civilizations to make rapid scientific and technological leaps. A strong new hunter can pose a threat to others, because advanced civilizations can start to be wary of it or seek to destroy it. However, Chao Yu points out that any invasion attempt could also harm the attacker, as other civilizations with similar or higher levels of advancement would be able to detect it, which would contribute to the chain of suspicion. However, in spite of the clear advantage in attacking other civilizations and in stealth, the DFH considers another scenario: benevolence.
The point of benevolence is to refuse to attack other civilizations, even if they are detected, and they will probably be able to respond to the signal. In a dark forest, this tactic is very dangerous because it is again reinforced by the chain of suspicion. Found by a benevolent civilization, another civilization may turn out to be aggressive or rapidly developing. Therefore, in the future, it will be able to destroy others and survive, having collected enough resources, whereas the benevolent civilization will most likely cease to exist. If we assume that extraterrestrial life really exists, and it is way more advanced than us, then it might attack us, since this is a survival tactic with the highest chance of success. This is not the best news. So then, are there other ways for the events to unfold that are beneficial for Earth based on the dark forest hypothesis besides an attack on our planet? Let's look at this in terms of game theory. Number 4, game theory and DFH. The point of game theory is to learn how people make decisions based on certain conditions in order to achieve the best result. So let's imagine Earth as civilization A and a more advanced alien life as civilization B. Let's assume that B has picked up on our radio signal. Now B has 3 strategies for action: attack, remain unnoticed but become suspicious, or respond with a prospect of possible friendship. Attack will be considered the most advantageous strategy, even if A is able to fight back. On the other hand, this scenario might turn out to be a losing one for B if A, according to researcher Alina Su, can send a signal in order to transmit the coordinates of the planet of civilization B to other civilizations. Perhaps in this case, the best option would be to remain unnoticed. If both civilizations don't do anything, neither will benefit. On the one hand, this will save A and B from danger, but on the other hand, they won't be able to obtain the necessary resources. There's also an option to make friends. If both civilizations agree to an alliance, then one of them will benefit, for example, from the ability to use alien technology. The other civilization, the one that proposed friendship, would also be able to benefit, albeit slightly less. Does that mean that an alliance is the best scenario for both civilizations? Possibly, but it comes with some caveats. Firstly, benevolence, as you already know, is very dangerous because, hypothetically, extraterrestrial civilizations are unlikely to be friendly too often. Secondly, the potential amount of resources that would be obtained, even if a trade deal is established, is less than what you would gain with a forced takeover. And so, the theoretical attack on Earth has the highest probability, but this course of events can greatly harm the attacker. Still, other civilizations may be afraid of the unknown military potential of Earth, and therefore choose the tactics of secrecy or friendship. 5. The danger of sending signals into space. Does it mean that if the probability of Earth being conquered is higher than any other option, should we be wary of the propagation of our signal into space? According to DFH, messages to other civilizations could threaten our security. The same opinion is shared by many astrophysicists, including Stephen Hawking. After a breakthrough in space research in the middle of the last century, there was plenty of interest from scientists in the search for alien civilizations. In 1974, the famous Arecibo message was sent to a star cluster 21,000 light-years away. Since that time, several radio messages have been launched into space, the latest of which dates back to 2017. Physicist Stephen Hawking believed that these messages could lead to the scenario described in the dark forest. According to him, an alien civilization visiting Earth could have the same consequences for us as the effects colonization of America had on its native inhabitants in the 15th century. Therefore, he expressed an opinion that this type of communication must be stopped. Nonetheless,
Other scientists, including SETI astrobiologist Douglas Vakoch, believe that the fear of sending messages can lead to Earth's isolationism. Moreover, Vakoch pointed out that the alien civilizations have had a chance to attack our planet while it was just developing, so you should not be afraid of the possibility of being heard by extraterrestrial life. Finally, the dark forest hypothesis also promotes the idea of differences in hunters' behavior. That is, not all alien civilizations would definitely attack us if they detected our signal. Additionally, a group of independent researchers led by the Global Catastrophic Risk Institute, Seth Baum, suggested that in addition to potentially dangerous civilizations, those with a lesser potential to harm us may also exist. They believe that there might be neutral civilizations that prefer to hide and not make contact, as well as civilizations that could establish a friendly relationship with Earth and help us solve global problems. In conclusion, the dark forest hypothesis is not the sole answer to the burning question, where is everyone? There are many other suggestions that attempt to explain the lack of a hint of extraterrestrial life, such as too great of a distance between civilizations, or the low likelihood of the emergence of other living organisms. Nevertheless, we cannot rule out the possibility of the veracity of Liu Cixin's theory, but we cannot confirm it either. Are we alone in the universe? Those involved in the search for extraterrestrial life have been increasingly sharing the view that mankind is not ready for contact with the alien civilization. It becomes obvious the moment we put the dreams and imagination aside and delve into the scientific approach. Not only can the search for intelligent civilizations be fruitless, but it can also lead to opening the door that we are not ready to walk through. What mysteries actually hide behind the cosmic silence? And why do we put so much effort into coming in contact with extraterrestrial beings, knowing that we may never achieve this goal? After spending years exploring the possibilities of coming into contact with extraterrestrial beings, scientists had come to surprising conclusions. Let's imagine that alien civilization is at the same level of technological advancement as us, and their spacecrafts fly at the same speeds as ours. Turns out intelligent life with this advancement level needs less than 1 billion years to spread across a galaxy of the same size as ours. Just look at how fast the galaxy would actually have been inhabited by any civilization of this caliber. But if that were the case, why are we not seeing this lively galaxy around us? To answer this question, we'll need to take a look at the Kardashev scale. The majority of modern scientists use this scale to measure the potential ability of living organisms to colonize the surrounding space and subsequently the possibility of contact with other life forms. This scale gives its own answer as to why we are not seeing this image of populated space all around us. Kardashev proposed to measure a civilization's level of technological advancement based on how efficiently it uses their energy resources. According to this scale, a Type 1 civilization can learn to utilize all of the energy that they're able to harvest on their home planet, radiating from its parent star. This type of civilization is most likely ready for interplanetary travel and at some point down the line will be able to colonize its entire system. For context, we only use 73% of the planet's energy potential, whereas the amount of energy we learn to harness from the sun is less than 0.1%. Turns out we're still on level 0, according to this scale. Civilizations that have reached the status of Type 2 are capable of capturing the energy not only on their home planet, but also any energy they could harness within their star system. Or at the very least, they're close to being able to do that. In their search for this type of civilization, scientists are on the lookout for a Dyson sphere,
a hypothetical artificial structure that would allow the civilization to harness all of the star's energy from within the system. These civilizations would be capable of interstellar travel. They will have actively colonized their own galaxy and possibly moved on to colonizing the surrounding areas, which would allow them to keep increasing the amount of energy that they could use. As well as using all of the energy of their star system, Type 3 civilizations are able to harness the energy from neighboring systems, control the energy of their entire galaxy, or even the entire universe. These civilizations are able to not only control this energy, but possibly change entire worlds. There's a simple reason as to why communicating with the Type 1 civilization is problematic. Upon calculating the capacity at which we can transmit and receive signals in space, we come to find that the maximum visibility of the Earth's energy activity, radio signals, lasers, electric activity, is very limited. We can only be seen or heard from a distance of 4 light years. The noise we create could only be heard by our closest neighbors who have reached the same level of development. Type 2 civilization would be able to hear us from much further away. They would also be able to ensure they remain unnoticed, either because of the great distance or because they wish to keep it that way. After 60 years of transmitting various signals and scanning the skies trying to detect artificial signals, we haven't been able to find anything and we remain unheard. The paradox of great silence was first raised by legendary physicist Enrico Fermi. Speaking to his colleagues once, he raised a seemingly simple question. Where are the aliens, and why have they not been to visit us? However, when you consider our civilization's level of development, the answer's pretty obvious. Why would they? The logistics required for interstellar travel are only available to civilizations that have reached Type 2 at least. And in their eyes, we're not worth it. What person in their right mind would try to communicate with ants? How would an ant be able to recognize that someone's trying to communicate with it? After all, in terms of our development and technological advancement, compared to them, we're akin to highly developed ants that have taken over an entire planet, not to mention the ineffective use of said planet's potential. Other civilizations that, like us, haven't yet reached Type 1, they stay confined to their own planet and star system. It's simply unrealistic to expect any guest from a place like that. It is possible that right at this moment they're working on the same problems as we are. Starvation, fighting for resources, and pursuing minor and major wars for territories. And so it appears that Type 1 civilizations would simply have other things to worry about. However, is it possible that someone could have overcome those issues and decided to launch themselves into space? The data presented by the scientists suggests we may in fact have a surprisingly large number of neighbors. As we lift our gaze to the cloudless sky, we can imagine how many potential inhabited planets there are. What we see in the sky is only 1% of our own galaxy, the Milky Way. Even if only 1% of these worlds are inhabited and populated with conscious life, that would amount to around 100,000 intelligent civilizations that could exist in our galaxy alone. And they all remain silent. There are a vast number of solutions to the Fermi's paradox, because there are around 100 scientific theories alone that attempt to explain this silence. Let's break down the most interesting of those theories. There are no signs of Type 2 or Type 3 civilizations because they don't exist. The scientific analysis tells us there are thousands of civilizations in our galaxy alone, hence they presume that there is a factor that stands in the way of their development. This factor is called the Great Filter. This theory suggests that after reaching a certain level of development, life faces an obstacle that's impossible to overcome. However, scientists don't know what this great filter may be. The possibilities are only limited by our imagination, from artificial intelligence, which cleanses the overly developed organic life from the galaxy, to various forms of apocalypse. The most unfortunate thing about this theory is that, if true, humanity is faced with three possible prospects in the future. According to the first scenario, we as humanity are a unique life form that has managed to overcome the big hurdle of the Great Filter. That would mean that reaching our level of progress is very challenging, and the chances of it happening are very low. In this case, the cosmic silence would be caused by the majority of civilizations failing to overcome the Great Filter. Hence, we simply have nobody to come in contact with. The second scenario suggests that we happen to be the first ones among our neighbors to advance to this level. This would be due to the fact that the conditions necessary for the existence of conscious life had only been established relatively recently, and we happen to be the pioneers of this progress. In this case, we simply found ourselves in the right place at the right time to have become one of the first ultra-intelligent civilizations. It also means we have plenty of time to advance to become a Type 2 and Type 3 civilization. That's the reason why there's no hope for contact. We are progressing faster than any other organic form of life since the Big Bang. The third scenario presented by scientists is more pessimistic. They reckon that if we were not the first ones to reach this level of advancement in this rare sequence of cosmic events, then the Great Filter is still ahead of us. They think that life evolves at regular intervals until it reaches a certain stage, which is where we stand now. Whatever or whoever it is, it presents a challenge that prevents life from evolving to a Type 1 civilization, and it's unlikely that we would be an exception to this rule. Those favoring the third hypothesis believe that the cosmic silence is great news for us. After all, the presence of complex life on Mars, Moon, or somewhere else means that the Great Filter is bound to be ahead of us. There's also an opposing viewpoint. According to it, Type 2 and Type 3 civilizations do exist, and we haven't come across them for a reason. This is based mainly upon the fact that we're very much limited in our search. After all, we are searching for the signals that are only 100 light years away from us, which represents a mere 0.1% of our galaxy. The most interesting theories resulting from this version sound like this. Galaxy has long been colonized, and to the colonizers themselves, we are located in a low-interest deserted area. The perfect example of a similar situation happened in Earth's history, colonization of North America. Native Americans residing in the remote parts of the continent only learned about the presence of their neighbors, super-developed Europeans, several decades after the latter arrived on the continent. It's also possible the activity is present around our system. We're simply too primitive to understand these signals, or we are focusing our efforts elsewhere. That would be like trying to communicate with people using the internet via Morse code. It is equally possible that our minds differ so greatly compared to other life forms that our attempts to establish contact come across as senseless noise. Another interesting hypothesis is the cosmic zoo theory, which states that we are actually surrounded by a densely populated galaxy. Within this world, Earth is something akin to a wildlife reserve, the kind you could watch, but you're not allowed to go on a safari ride or make contact with such a primitive life form. And still, every attempt to explain this paradox inevitably comes to a stop. We still know very little about space, and we have not yet evolved to the level necessary for resolving these problems. But that doesn't mean that our attempts to find intelligent life have stopped, and humanity is frozen in place, waiting for outside contact. There are currently at least 2 projects that have spent several decades trying to establish contact and search for extraterrestrial life. These are the projects SETI and METI. The work of these 2 projects is based on the Drake equation, a mathematical formula that suggests it's possible to accurately calculate the number and more importantly, the potential location of inhabited worlds. The next step is to use this information to reach out. According to this equation, our galaxy hosts between 8 and 2,900 systems of intelligent life. As science evolved and our knowledge about our galaxy grew, the calculations became more precise. Realistically, there should be 36 other brother worlds coexisting with us in the Milky Way galaxy. The SETI project started in 1984, and at first it focused on scanning our immediate surroundings in search of artificial radio signals coming from our potential neighbors. However, no signals were found. Right now, the major hope is that the European Space Telescope Gaia will bring some results. It's able to transmit information about the exact location of all stars in our galaxy and give an accurate assessment of every star system's potential. That's why the SETI project was able to move on from a rough estimation of various star systems to a detailed analysis of each one, thanks to a technological advancement. And now, every signal sent out there is directed towards the systems with the highest likelihood of intelligent life. Will we get a response from any of them? The answer to this is both yes and no. Some of the systems we have already researched are so far away that any response from them would take over 3,600 years to reach Earth. And last but not least, the mission of METI is also very important. After all, they help by trying to capture any messages from space and send our greetings to distant stars. We know of at least 8 attempted communications, 2 of which are the famous gold records on the Voyager probes and similar ones on the Pioneers. The other 6 are messages contained in radio signals directed towards some stars. For example, to one of the nearest solar-type stars, Gliese 581. So far, there have been about 40 radio sessions in total. We're unlikely to hear a response to them, but it is possible that our descendants might. To sum up the results of our small study, we can say quite definitely that the silence of the universe is normal. It's also possible that we have not yet sufficiently evolved to make contact with the intelligence around us, or even that the cosmos itself is not yet ready for this. Which one of these scenarios is the most likely? Are we a unique species, or has the entire space been colonized by super-developed civilizations for a long while? We are close to uncovering the answers to these questions. But are we ready for this contact?
All of us probably watched science fiction films and wondered what aliens may look like. Many people imagine extraterrestrial life similar to us, carbon-based, but with a few biological differences. And others imagine it as something completely unlike humans. And so the famous author of The Laws of Robotics, science fiction writer Isaac Asimov, describes some forms of alien life as living stones that had a silicon-based chemical composition as opposed to carbon like us. But what if we told you that silicon-based life may not be entirely fictional? Today, we will delve into our biology and try to answer whether the existence of silicon-based life is possible. Carbon is the basis of our life. Without it, it is possible that we would never have come to exist. It makes up about 18%, or 26 pounds of our total body weight, and performs a structural function, forming something akin to a carcass for the molecules and organic substances necessary for our life. Proteins, fats, carbohydrates, sugars, etc., even DNA. Moreover, as you may know, carbon plays an important role for many life forms around us, such as plants. With each breath out, we exhale carbon dioxide. This gas is required for plants for photosynthesis and the production of oxygen as well as organic substances like glucose. CO2 is also the gas that traps heat in our atmosphere, which sustains all life on Earth. If it weren't for the harmful greenhouse effect, we would simply freeze. Aside from the value of carbon and its compounds in biology, it's important to mention the role it plays in manufacturing. Most of the things you see on a daily basis contain carbon. From clothes, medicine, your favorite cup of coffee, and the house you live in, to musical instruments played by your favorite musicians, and the phone or laptop on which you're watching this video. All of it couldn't exist. Of course, carbon is not the only component present in living organisms and all of the aforementioned items, but its chemical versatility and the ability to build huge chains with other elements makes carbon practically indispensable. According to astrobiologist Robert Hazen, a vital chemical element must be able to actively form bonds with other elements and not be too reactive at the same time, so as not to combust during these interactions. Furthermore, this element must form strong, long-term bonds and be able to store and transmit information. Carbon meets these criteria, therefore is superior among the most important building blocks on Earth and beyond. However, is carbon really the only possible foundation for life? What if it was simply erased from outer space? What element could then replace carbon? The possible answer can be found right under carbon in the periodic table: silicon. Silicon is one of the most common elements on Earth. Its core contains about 28% of its total mass. This element can be found in sand, amethyst, clay, granite, etc. Like carbon, silicon has a wide range of applications and is a valuable element in our life. Many processors in phones and computers use silicon as an accessible alternative. Silicon is also used to form conformable silicone compounds, which have applications in cosmetic and medical industries, ranging from hair conditioners to contact lenses, as well as aviation and construction spheres, like in sealants and nonstick paint. So what role does silicon play in our biological life? According to researcher Milton Wainwright, it's likely that silicon may have had an effect on the emergence of life on Earth. According to his research, silicon that comes from outer space may stimulate bacteria growth, even if there's a lack of nutrients. The scientists therefore suggest that billions of years ago, during the birth of the solar system, comets containing silicon may have bombarded Earth, which caused the development of bacteria. In addition to its possible merits in the past, silicon is also a very important component in plant development and growth. Silicon protects plants from external threats, both physical and chemical, making them more resistant. It also protects the plants from disease and prevents them from losing water. Moreover, silicon is important for healthy bone development and wound healing in humans and other animals. This element may also reduce the risk of Alzheimer's and cardiovascular disease. You could say that silicon, in fact, has an auxiliary effect on our lives. So why is it being considered as a likely alternative for carbon in alien life? First, it is due to their chemical similarity. There is a reason why silicon is located right under carbon in the periodic table. Each chemical element in the table can form a chemical bond, during which the electrons of each atom are combined. Silicon and carbon are both tetravalent, meaning they can bond to 4 atoms. As such, silicon can probably form long and strong bonds with different elements, similar to carbon. Secondly, in 2016, a team of scientists from the California Institute of Technology, led by Francis Arnold, were able to synthesize molecules that are made entirely of silicon and carbon. Furthermore, according to their study, E. coli could produce the protein that contained this compound. Scientists came to the conclusion that silicon-based life is possible outside of Earth. So,
In order to answer the question of whether silicon could replace carbon, we must first consider what life is in biological terms and what are the criteria for it to occur. Scientist Norman Pace believes that life is the ability of an organism to replicate itself and to develop enough to overcome evolutionary hurdles. For example, developing the ability to grow organs required for movement in order to make travel across land easier. Therefore, the building blocks of this organism must be able to quickly adapt to new conditions. In addition to chemical complexity, a number of ecological criteria must be met for life as we now know it to emerge. In short, life requires oxygen, nitrogen, moderate temperatures, and water. Many compounds are highly soluble in water, such as salt. Therefore, previously separate parts of one compound can create new bonds with other elements. Carbon can form a long and stable framework for the living cells of water-based organisms. But can silicon also make connections necessary for life to exist? The short answer is no. So, what? That's it? Silicon-based life cannot possibly exist? Not quite. Because in addition to water, there are other solvents in which life can hypothetically originate. For example, scientists speculate that liquid ammonia, which is common on Jupiter and Pluto, could serve as an alternative to water. However, NH3 is highly toxic, which may prevent silicon-based life from developing, but scientists have yet to test this theory. In addition to liquid ammonia, another potential solvent is sulfuric acid. You may note that H2SO4 is generally capable of dissolving most metals without residue, and you'd be correct, but oddly enough, it's also possible for silicon to develop in it. Therefore, hypothetically, silicon-containing organisms can develop on planets with a sulfuric acid environment, such as Venus. Silicon can also exist in other cold solvents like methane and ethane, which become liquid at low temperatures, as they do on Titan, one of Saturn's moons. However, low temperatures greatly slow down any chemical processes and solubility. Although silicon would be able to quickly combine with other elements at low temperatures, silicon compounds would not be able to dissolve very quickly. Therefore, it would be very difficult for life to emerge in such conditions. But what about the structural function of silicon? Just like carbon, silicon can combine with elements essential for our existence, including nitrogen, hydrogen, oxygen, phosphorus, sulfur, and even many metals. However, silicon is not as versatile and adaptable as carbon. In addition to the fact that silicon cannot develop in water, it will also not bond with anything at moderate temperatures between 32 and 212 degrees Fahrenheit. That means that silicon can only combine with other elements at excessively high or significantly low temperatures, which would make it very difficult for other elements to build bonds with silicon. Moreover, unlike carbon, silicon does not bond well with itself, and that is the bonds between two silicon atoms that would not be able to build a very large framework for cells. Think of a diamond. It's made entirely of carbon, which shows the strength of the compounds the element is able to form. However, the one element that silicon likes to combine with is oxygen. And this further supports the theory that silicon-based life is unlikely. On Earth, silicon is almost always found in the form of SiO2, which is basically sand, making it very difficult to separate the two elements. This means that silicon is less versatile than carbon, which forms equally strong bonds with other elements. Turns out that if we could swap carbon in our body for silicon, then instead of carbon dioxide, we would exhale sand. Aside from respiration, carbon also plays a very important role in our nutrition. Food is an excellent source of energy, which is why when we feel tired, there's nothing better than a good meal. However, our source of energy is not the food itself.
but the compounds it contains, like glucose. As you may have already guessed, glucose is also made of carbon. What's more, when we don't have an opportunity to eat and we need energy, another carbon compound like starch can help us. It's deposited into the liver and used to replenish our supply of glucose when needed. However, these bonds would be unstable with silicon, which means they would not be able to properly support our life. While silicon is unlikely to replace carbon, it is possible for silicon-based life to evolve. However, it's highly doubtful that an organism that only contains silicon and no carbon in its chemical composition would be able to build complex chemical bonds. Silicon-based organisms have not yet been found on Earth, but as we've already mentioned, silicon is an important secondary component for many plants and animals. In some ways, it could probably be considered a part of ourselves. Furthermore, our ocean contains diatoms, a type of mysterious algae with cell walls made of transparent SiO2. This doesn't make this algae a silicon-based life form, but it does prove that silicon can indeed act as a building block of a living organism. As for other planets, according to a study by a team of scientists led by Ricardo Gobato, the ideal environment for the development of silicon-based life are the virtual absence of oxygen and water, temperatures above 428 degrees Fahrenheit or below 32 degrees Fahrenheit, atmospheric pressure much higher than on Earth, and a solvent like sulfuric acid or methane. Some of the planets in the solar system fit some or almost all of the criteria. For instance, Titan, the largest moon of Saturn, and possibly Venus. Titan has a multitude of methane and ethane lakes, as well as a nitrogen atmosphere, which are both excellent conditions for the origin of silicon-based life. The surface of Venus is very hot and subject to high pressure. However, the thing that makes Venus one of the candidates for silicon-based life are yellow clouds of sulfuric acid present on the planet. Hypothetically, silicon organisms could form in these clouds, although most likely, even on Venus, a molecule like that would contain significantly more carbon than silicon due to the high content of carbon in the atmosphere. Surprisingly, another candidate for the formation of silicon-based life are hypothetical carbon planets. At the moment, scientists only know of one such exoplanet, 55 Cancri E, which is located 40 light-years away from Earth. These planets likely form further from their parent star, which means they may have solvents suitable for silicon on their surface, and hypothetically, no water either. Moreover, it is possible that carbon planets are full of heavy hydrocarbons like butane, which may be suitable for silicon-carbon bonding. However, silicon-carbon compounds, silicon carbide, are very strong, which means their decomposition can take a lot of time and energy. So even if life begins to develop on a carbon planet, it will be a very long process. If we assume that silicon-based life has in fact existed for some time, then how would we recognize it? Sci-fi writers imagine a life form similar to living stones, like the authors of the Star Trek, for example.
We are dealing with a silicon creature of the deep rocks.
However, in reality, silicon-based life does not necessarily look like this, since we are also not covered in diamonds and diatoms look nothing like stone. The fact of the matter is, scientists have no idea what a silicon-based life might look like. However, they assume that silicon-based life is unlikely to resemble us in chemical complexity or even intelligence, so we probably won't get to meet stone people. Such alien organisms would also be difficult to find if not technologically advanced, because we simply would not know what molecules to look for. It is difficult for humans to imagine the possibility of life developing in conditions that are significantly different from those on Earth. The only life we've encountered so far is ourselves and the creatures surrounding us, which is why most missions sent into space focus on finding structures similar to our own. Right now, it's impossible for us to know if there is life made predominantly of silicon due to our scientific limitations. However, the cosmos is vast and diverse, so we cannot say for certain whether all alien life in billions of galaxies is carbon-based.
Imagine that you're standing on the edge of a boundless ocean with a sparkling cosmos reflected in its waters. Now imagine that this panorama, with its myriad stars and spinning galaxies, is just a reflection, a projection from an invisible distant shore. This is not the beginning of a science fiction tale, but a look at one of the most striking theories in modern physics: the holographic principle. Just as each droplet on a spider's web contains the world in miniature, our universe may be a grand reflection of fundamental laws written on a distant frontier. Far from the solid earth beneath our feet and the emptiness of space, the very fabric of our reality may be generated by something much deeper, something beyond our present comprehension. Let's go on this exploration together and try to answer the ultimate question: does the fabric of our universe arise from a holographic boundary? At the heart of physics is a quest to uncover the layers of reality to reveal its most fundamental elements. These elements, known as ontological primitives, are the foundation upon which the vast edifice of the universe is built. For centuries, physicists have searched for these building blocks, seeking to understand the rules governing their interactions. The journey begins with the concept of space. Isaac Newton, one of the titans of science, envisioned space as an absolute, unchanging background, indifferent to the comings and goings of matter and energy. For Newton, space was an absolute receptacle, an infinite space in which all the events of the universe were played out. However, as our understanding deepened, this view of space began to evolve. The advent of Einstein's theory of relativity painted a different picture, in which space was not just a passive arena, but an active participant in cosmic interaction. According to the new view, space could bend and curve in the presence of mass and energy, calling into question the very notion of its absoluteness. Amid the shifting perspectives, a radical idea emerges: the holographic principle. This principle suggests that our three-dimensional perception of the universe may be akin to a hologram, a projection from a two-dimensional surface located at the edge of space. This edge, though indefinitely distant and inaccessible to direct observation, may contain the fundamental information that gives rise to everything we perceive as reality. This concept overturns our usual notions by arguing that the very essence of space, the fabric of our reality, may not be a fundamental characteristic of the universe, but is emergent. Emergentism describes phenomena that arise from the complex interaction of simpler elements, leading to new properties and behaviors that are not obvious based on the components alone. In the context of our universe, and especially within holographic principle, emergentism takes on a fascinating role. Here, the term implies that the three-dimensional space we move through and the time we experience are not the fundamental building blocks of reality. Instead, they arise from a more basic or two-dimensional structure, the holographic boundary that encodes the information and laws that give rise to our perceived reality. In this framework, every star, planet, and galaxy, every law of physics from gravity to electromagnetism, and the very fabric of the cosmos are emergent phenomena. It's something like a bridge between the known and the unknown, between the observable dimensions of our universe and the fundamental coding of reality at the holographic boundary. It invites us to rethink not only the structure of the cosmos, but the very nature of reality as we peel back the layers of the universe. Against the backdrop of our hypothesis, black holes, where gravity triumphs to such an extent that even light cannot escape it, have become those unexpected heroes, thanks to the pioneering insights of Stephen Hawking and Jacob Bekenstein. Hawking and Bekenstein ventured into uncharted territory by attempting to combine the fields of quantum mechanics and general relativity theory in order to explore the thermodynamics of black holes. Their theories revealed the startling fact that black holes are not absolute endpoints of entropy, but rather key players in the cosmic interaction of information and energy. Entropy, traditionally associated with disorder in a system, took on a new dimension in their hands. It became a veil, hiding information inside black holes. It was not just about the randomness or disorder of particles, but about the hidden layers of information that define the very structure of reality. As matter spirals into a black hole, it seems to disappear from our universe, which raises a major question. What happens to the information it carries? This question calls attention to entropy, not just as a measure of disorder, but as a key to understanding the fate of ingested information. The entropy of a black hole, as proposed by Bekenstein, is directly proportional to its surface area, not its volume, a concept that contradicts our everyday understanding of physical laws. This relationship between surface area and entropy leads us to a profound conclusion. The maximum amount of information that can be contained in any given region of space is determined not by its volume, as one might intuitively assume, but by its surface area. This view laid the foundation for the holographic principle, which assumes that all the information of a volume can in principle be encoded on a two-dimensional surface. Thus, Hawking and Bekenstein's discoveries of black hole thermodynamics suggest a cosmos in which the very fabric of reality, every particle, every force, and the very dimensions of space and time can only be emergent properties emerging from a deeper two-dimensional fabric. At the forefront of bridging the gap between the mysteries of black hole thermodynamics and the holographic principle is Juan Maldacena. This work is not just a framework, but a concrete example of holographic principles in action. Maldacena's correspondence asserts a duality between a type of space known as anti-de Sitter space, abbreviated ADS, and conformal field theory, or CFT, which exist at the boundary of this space. Despite the positive cosmological constant of our universe, which contrasts with the negative constant of ADS space, the principles derived from this duality provide insight into the nature of gravity and quantum mechanics, and by extension, the holographic nature of our universe. Central to this dualism is conformal field theory, which operates on the boundaries of the universe within the ADS-CFT framework. CFT is unique in its scale and variance. The laws governing these field theories remain unchanged regardless of the size or scale at which they are observed. This property of CFT is key because it encodes the information needed to describe higher dimensional bulk space within a lower dimensional framework, effectively illustrating the holographic principle. Scale invariance within CFT is not just a mathematical curio. It is a window into the emergence of dimensions and the very fabric of space itself. Different scales of patterns at the boundary governed by the uniform laws of CFT, contribute to the illusion of three-dimensional space. This phenomenon emphasizes the holographic principle that the complexity and dimensions of volume space arise from simpler, scale-invariant dynamics at the boundary. Through the prism of ADS, CFT, and the intricacies of conformal field theory, we gain a deeper understanding of how the dimensions and the very structure of space-time can emerge. Scale-invariant boundary patterns each contributing to the holographic encoding of the universe. One of the most obvious metaphors for this complex idea is the concept of nested spheres. These nested spheres serve as visual framework, with each layer representing different scales of boundary patterns. The finest patterns, akin to the microscopic level, are densely packed with information and require high-resolution understanding. As you move to finer spheres, the patterns become coarser, encapsulating the same information but in a more generalized, less detailed form. In the microscopic space of the holographic boundary, the patterns are dense and highly detailed, resembling the fine strokes of a master painter. These fine-grained patterns are the most fundamental level of the universe, where every tiny element is filled with information encoding the laws of physics and initial conditions of cosmic phenomena. Moving from the micro to the macro environment resembles looking at a mosaic. Up close, we see only individual tiles, each with its own color and shape, but at a distance, a complex and holistic image emerges. Similarly, the grand structure of the universe, galaxies, stars, and planets, emerges from this collective behavior of fundamental patterns encoded on the holographic boundary. This transition from fine to coarse-grained patterns at the boundary of the universe is not just a feature of the holographic model, it's a fundamental process that shapes our perception of space. It emphasizes the differences in information requirements at different scales, demonstrating the adaptability and efficiency of the holographic encoding of space. The concept of a holographic universe is based on a profound philosophical and scientific notion, ontological democracy. This idea suggests that the boundaries of the universe, with its two-dimensional encoding of information and the three-dimensional space we're familiar with, can be equally fundamental to the fabric of reality. Neither is more real or primary than the other, rather they coexist in a state of mutual emergence. This view has far-reaching implications. It suggests that what we perceive as the three-dimensional reality of stars, galaxies, and planets, all with their complex interactions, may be the manifestation of deeper, more fundamental laws encoded at a distant and visible boundary. Now, this coding not only dictates the structure of the volume, but is also shaped by events within it, creating a feedback loop. In our journey through the holographic universe, we encounter a profound rethinking of gravity, which is traditionally viewed as the curvature of space-time under the action of mass. In the holographic framework, gravity arises not from the mass itself, but from entropic forces acting in the information encoded at the boundary of the universe. Now, the idea that gravity might be an emergent phenomenon like temperature or pressure in thermodynamics represents a radical shift in perspective. It suggests that what we perceive as gravitational attraction is the result of the universe's tendency to maximize entropy, an idea first proposed by physicist Eric Verlinde. This theory suggests that gravitational attraction arises from changes in the amount of information associated with the position of material bodies. The holographic universe also pushes us to explore the mysterious role of quantum entanglement in the fabric of space-time. Quantum entanglement, the phenomenon in which particles remain bound in such a way that the state of one particle can instantaneously affect the state of another, regardless of the distance separating them, may be the thread that weaves this spatial continuum of the universe. According to this view, space itself arises from the entanglement of quantum bits encoded at the cosmic boundary. When particles are entangled, they share a common bond that contributes to the illusion of continuous space. Theoretically, unraveling these particles could lead to the disappearance of the space between them, which calls into question the very notion of distance and locality in our universe. The principle of a holographic universe, of course, like many other theories in physics, poses one ultimate question, the question of finding a universal holographic model. This ambitious endeavor is designed to reconcile the myriad complexities of the universe into a single structure that accurately describes both the immense cosmic scale and the minutiae of quantum mechanics. The challenges in this endeavor are enormous. Creating a universal model requires not only a deep understanding of quantum mechanics and the general theory of relativity, but also a new approach to integrating these theories into a holographic framework. Potential breakthroughs promise to revolutionize our understanding of the cosmos. A successful universal holographic model could provide unprecedented insight into the origin of the universe, the nature of black holes, and the fundamental laws governing reality. As we journey through the possibilities of the limits of this theory, we may be on the threshold of a new understanding of the cosmos or another refutation of high-profile theory. If reality is holographic, then our perception, experience, and very existence may be far more intertwined with the cosmos than we ever imagined. This journey is fraught with challenges and unknowns, but the promise of unlocking the deepest secrets of the universe propels us forward in pursuit of an elusive, universal model that would redefine our place in the cosmos.